Geometry might be far more dangerous than you think. What if I told you that the rule you learned in school, parallel lines never intersect, is not valid in most of the universe? First, we see a flat surface. This is flat space, Euclidean geometry. Here, everything works according to the rules we are used to. To understand how geometry relates to dimensions, let's look at two dimensions. A square appears on the screen, and inside it, a point is moving. This point can only move in two directions, forward, backward, and left, right. Only two directions. There is no third direction. That is the limitation of a two-dimensional world. Now, two straight lines are drawn on this plane. They extend infinitely. No matter how far they continue, if they start out parallel, they will never intersect. In Euclidean geometry, parallel lines do not meet, not even at infinity. Then a triangle appears, familiar from school. Its vertices are labeled alpha, beta, and gamma, and we know that the sum of its interior angles is always 180 degrees. This result never changes, because we are on a flat plane, because we are in Euclidean space. Everything we have seen so far belongs to plane geometry, Euclidean space. Now we move from flat space to curved space. This is where we enter the world of Riemannian geometry. Bernard Riemann was born in 1826 and died in 1866. At a remarkably young age, he showed that geometry does not have to be limited to flat surfaces. In his famous 1854 habilitation lecture, he demonstrated that space itself could be curved and that this curvature could be described mathematically. His goal was to understand the foundations of geometry in a deeper and more general way. In Riemannian geometry, curvature can vary from point to point. Space does not have to be homogeneous. It can be flat in one region and more curved in another. The fundamental object that determines this structure is the metric tensor. The metric tensor defines how distances between nearby points are measured. It is, in a sense, the measuring rule of space. Euclidean geometry, spherical geometry, and hyperbolic geometry are all special cases of Riemannian geometry. Riemann's framework is the more general structure that encompasses them all. When the metric changes, distances change. The shortest path between 2 points is no longer necessarily a straight line in the usual sense. Now we see a sphere. Consider lines passing through the poles. At the equator, they may appear parallel, but they must intersect at the north and south poles. On a sphere, there are no truly parallel straight lines. The straightest possible lines, great circles, always intersect somewhere. Now we see different curved surfaces, a sphere. A hyperbolic paraboloid, a saddle-shaped surface. A torus, a donut-shaped surface. A Mobius strip, a one-sided, one-edged surface. A helicoid, a surface rising like a spiral ramp. A catenoid, a minimal surface resembling a soap film stretched between two circles. And Enneper surface, a self-intersecting minimal surface. Now we move to geodesics. On the sphere, we see the shortest paths between two poles. The yellow curve represents a geodesic. A ball moving along this curve follows the shortest possible path. On a sphere, the shortest paths are arcs of great circles. Immediately after, a red curved path appears. It connects the same 2 points, but it is not the shortest path. Curvature determines which path minimizes distance. Now parallel transport and holonomy. An equilateral triangle is drawn on the sphere. A vector is transported along the edges of the triangle. When it returns to its starting point, its direction has changed. It has rotated by 90 degrees. In spherical geometry, this is possible because the surface is curved. On a flat plane in Euclidean geometry, this same process would leave the vector unchanged. Curvature manifests itself almost like a physical effect. Let us return to the sphere. In spherical geometry, you can draw an equilateral triangle where each interior angle is 90 degrees. The total sum of the angles is then 180 degrees. The reason is positive curvature. Now we see three surfaces together: the sphere, the plane, and the hyperbolic plane. The hyperbolic plane curves inward like a saddle. On all three, we draw equilateral triangles. Clearly, the triangle on the sphere has the largest sum of interior angles. On the plane, the sum is exactly 180 degrees. On the hyperbolic plane, it is smaller than 180 degrees because negative curvature reduces angles. And now we arrive at space-time. When a massive object appears, space-time bends. As the surface curves, a yellow circular path forms above it, and a yellow sphere moves along this path. What makes objects orbit one another is not a force, but the geometry of curved space-time. The door that Riemann opened was not merely abstract mathematics. It is the foundation of how we understand the structure of the universe today. Geometry is no longer just about shapes, it is the language of reality itself.